To Physics 9B. I'm wearing my headphone because I need to record nice audio so I can hear you. Don't worry about it. My name is Hsing-Yi. Hsing-Yi is my first name. Lai is my last name. You can call me Xing for short. I go by Xing. So let's go straight into the important thing. If you look at the pink Canvas page, you will see that your grade for this class will be 5% iClicker. So make sure you can have the iClicker app on your phone. The link is on Canvas page over here, or you can search for Physics 9BC. So that's the name I put for the iClicker for this course. There's a space, I believe, between y and 0. Okay, so 5% iClicker. You only need to respond on iClicker to get credit. It's not graded on correctness. You do have to respond to 70% of all the iClicker thing for the entire quarter to get those 5%. So you can miss a couple of lectures, it's fine. And you do need to get 70% of all the iClicker questions. So that is 5% iClicker. This is confusing me. Okay. Then you have 10% homework. Homework will be graded both in correctness and effort. We have a lot of students here, but we only have one grader. He is also your discussion TA, correct? So we don't have so many time to grade all the questions. Therefore, what we will do is to give you 2 points if you get a correct answer and all the detailed derivation explanation. If you have anything wrong, we won't tell you which part is wrong. We'll just deduct your point and then give you 1 point effort. If you put down nothing, you get 0. But you only need to get like 70% of all the homework questions for the entire quarter to get this 10%. So I hope that works for you guys. Then, also, first homework due next Tuesday on Grayscale. Submit your homework on Grayscale. You can see there's already homework 1. So do that. Then we have 20% discussion. So later today, some of you will have discussion, some of you have it tomorrow. The way we run discussion is to have you guys work on the board with some question you will only know at the day of the discussion. Garrett will hand out paper copies for you guys. For those questions, you should try to work on them because you will be tested immediately. Some of you will have to take a test today already. Those 20% are all from the test, which is directly related to the discussion that day. So you go to discussion, try to learn those materials as soon as possible, and then you'll get immediately tested on it at the last 10 minutes. The test is on Canvas. So at the last 10 minutes, go to your Canvas, bring a device. If you don't have device today, we will print out paper copy for you, but please bring your device in the future, and then just do the problem. So you will have some problems, multiple choice, and those accounted 20% of your total score. So even though this is like a test, but you only need to get 50% of those discussion tests to get this 20%. So you can miss some discussion, you can make some mistake in your test. You only need to get half correct to get this 20% for, okay? So from this iClicker to discussion, I designed it such that you can basically get all of them if you just show up and do your thing. Okay? Then there will be 25% midterm and 40% final. Any questions so far? Okay, so the next thing is good news. Good news. Good news. Your grade will not be curved. So this is a small class. There's only like 50 students. There's no way this grade have to obey any distribution. Anything can happen. If I curve you, I will have to make sure I don't teach you well, so you don't understand things, and you did bad job on the exams, so I can curve you up. That's how grading system works. If I don't curve you guys, then it is possible that you all learn really well and you all work hard and everybody gets A. I can give you all A's. I don't care how this distribution looks like. There's only 50 of you. Also, I'm not a professor. I'm not faculty. I'm just a grad student. They cannot fire me. They have to expel me. And they're not going to do that no matter what I do to this guy. So it's not going to be curved. And this, all right, so look at the rest of the canvas site yourself. Any questions? Yeah? It's cute. It's my popper. Any other question? All right, let's get straight into the lecture for today. So the way I organize this class is I separate the class into two parts. In the beginning, I want to give you a intuition of how to do physics, just the overall intuition. I will try to do as little calculation as possible. You will learn the mathematical detail in discussion. Those will be in your midterm, but in the lecture, I will just tell you the physics without doing math. So you can learn the physics, not the math. So that's why before your midterm, I will already go through chapter 1 until chapter 7 by October 17th. So I will go through everything without doing the math first, and then teach you the math in the second part. The midterm will be a lot easier than the final because there's no math. I will combine, your discussion will be in your midterm, so there will be some math, but they won't be combined. I will combine them for the final, for the second part of the course, but for the first part, it's just going to be the physics, so it will be, I hope that will be easy for you guys. Okay, so first thing we're going to talk about is wave. This is a wave. You see water in the tank, and the wave is going to the right. Now, this is called a water wave. This is one phenomenon we're interested in 9B. In 9B, we look at things that just involve a lot of particles. You cannot say one particle is moving anywhere because this phenomenon involves a lot of particles together. Now, let's practice your eye clicker. Take out your eye clicker. When you see this icon, it's your eye clicker. And I have to open the eye clicker. Oh my god. I forgot the eye clicker. Give me a second. How can I start the eye clicker without opening my eye clicker thing? Okay, start class. Is it floating somewhere? It's not floating here. Oops. This is not what I want me to do. Well, I guess some of you can respond already. I do see one respond, even though you don't see my clicker icon. And oh, it's here. It's here. Oh my god. Wait, what happened now? Yeah, yeah. Okay. Alright, so I screw up. I put a true and false, and this is multiple choice, but this is fine. I will make sure I pick true or false next time. Okay, so here's what we're going to do. If you have technical issue, if you don't have iClicker yet, or you have trouble logging into the class, I will stop the response, and what you're gonna do is to take a selfie with this result for every iClicker question and send it to me. Then you'll get credit for this one. Do that for every question, so I can make sure you're always here. You didn't leave early. I think it's important to learn how to take a quick selfie in 2024. So do that if you have technical issue. All right. So the first question is whether the water is moving as the wave is propagating. In the previous video, we see the water wave, but is the water actually flowing? So here you see there's also water wave going to your left, but the ball is not flowing. This is another animation which explains the situation clearer. So you see, as the wave propagates outward, the thing flowing on the water doesn't really go outward. This is because the wave is a disturbance of the matter around its equilibrium position. It's not really moving all the way to the right. It's just oscillating around its stable position. So these are the water molecules. What they're doing is just oscillating or wiggling around a fixed position. They are not really moving all the way to your right, but together it looks like something is going to the right. The pattern is going to your right, but nothing is actually flowing. Every single particle is just doing something around a fixed position. The position or the stable position of the particle are fixed, but together the wave pattern looks like it's moving to the right. This is the nature of wave. It doesn't transport matter. The matter is not actually moving to your right. It transports something else, which we'll figure out later. So that is water wave. You can also have similar phenomenon on a string. So this is a string wave. You can pull a string, and then it oscillates. This is kind of hard to see, so we do slow motion. You can see the wave travel back and forth on the string. Okay, so this is string wave. Now, we said that the thing is not actually moving with the wave. The thing is just oscillating. So, if I have this string wave, and I put a bow tie on a part of the string, the bow tie is fixed to a string, and I start a small wave, how will this bow tie move later when the wave propagates to the right? Open your iClicker. This is a real multiple choice question now. Where's my clicker? Here. Come on. All right. Go ahead and put in your answer. Do you think the bow tie will move up and down, to the right, to the left for whatever reason? Circle, clockwise or counterclockwise? Let's affect your thinking by showing other people's answer. Okay. All right. So again, if you have technical issue, just take a selfie right now. Let's review the answer. As the wave propagates, the bow tie move up and down. So in the previous video, you see a water wave have all the particles moving in circles. But for a string wave, it's easier. You just go up and down. But all the particles go up and down in different order. So together, it looks like a pattern is traveling to your right. Another example is like this. You can have my arm, and then you can have a wave. So a wave is going to your right, but my finger is always here. My other shoulder is over here. I just create a pattern and looks like something going to the right, but nothing is actually moving. Now, you learn, okay. So, now let's guess. What do you think will affect the speed of this pattern going to your right? Here we can have a short answer, so just type whatever you think. And we can have a word cloud. Yay, so fun. So go ahead and type in what you think will affect the speed of this wave. We do see a pattern moving to the right, even though all the physical particles are staying around its equilibrium position. And but we do have a pattern. We can have someone to look at the position of the pattern at each time and define a speed of the wave. So there should be something affecting the speed. The speed cannot be a random number. Let's see if it can be bigger. Oh. Okay, good. So we have force, string. The string affect itself. Good. Tension. Tension is a force. That's a good guess. Wave, mass. The wave affect the speed of wave. Okay. All right. So let's review the answer. So remember, in the video, you pull a string, and then the strings bounce back. Why does the string bounce back? Because the string itself has tension force. The force is a correct answer. Tension is a more specific answer. But the reason that this wave propagates is because the string wants to bounce back. And the bigger the tension the string has, the bigger the force. So if I have a bigger tension force, the string will want to bounce back faster, and that gives you a faster traveling wave. So if the string itself has a bigger tension on it, it's tighter, you pull the string really tight, the string wave will travel faster. But you learn that F equals ma, with the same force, the inertia of the object can affect the response, the acceleration. In this case, the inertia of the string is characterized by the linear mass density. Because we can have a long string which is heavier than a short string, but if you pull it equally tight, the speed of the wave should be the same. Therefore, the total mass of the string is not a good quantity. You should look at the density, just like when you say water is heavy, or when you say oil is lighter than water, it doesn't mean we are not really saying a bucket of oil is lighter than a cup of water. You are saying the density of oil is lighter than the density of water. Here, we are just looking at a string, so the mass that we care about is the linear mass density, the amount of mass carried by a unit length of string. You divide the total mass by the length, then you get a number that is truly meaningful for the speed of wave. So, any questions so far? So I think I forgot to mention, if you, how do I get rid of here? If you, yeah. So if you stop me and ask question during lecture, I will buy you mochi nut. The way it works is that you just go to this Google Excel sheet and put down how many questions you ask. And at the end of the day, we just count how many questions you guys asked in total as a class. And then you share the mochi nut like communism, because, yeah. So what is mochi nut? It's basically donut, but a mochi nut has a nice property which can easily be shared into 8 pieces. So just in case we have too few mochi nut that you don't get integer amount, you can have fractional number, okay? So I encourage you to ask question. You get mochi nut. All right, back to the lecture. So how can I give you question if you are just not doing math? That's not how physics 9 works, right? Well, just by the physics, there's something very important called dimensional analysis and analyzing the tendency. So what I'll give you is some question like this. I tell you F is the tension force on the string, L is the length of the string, mu is the linear mass density, the mass of the string by unit divided by total mass, total length. G is the gravitational acceleration, 9.8 meter per second square. And I want you to look at these three formula and see which one might be the correct formula for the speed of the string. You don't need to do any calculation, but if someone gives you a formula sheet telling you the speed of the string wave is extension divided by mu, you should think twice before you actually use this formula. One is that the tendency should match. Two is that one is that the dimension should match, and two is that the tendency should match. So what exactly does that mean? In physics, there's only three types of quantity: time, length, mass. You might see in different units for the same type of quantity. You can use second to measure time, minutes or hour also measures time, and year is also measuring time. The unit can be different, but the physical meaning is the same. It's just time. So this time is what we call the dimension of a physical quantity. And we use this symbol. The square bracket means we don't care about the number. We just care about what type of physical quantity it is. In this case, it's time. And then you have length. Some of you might heard meter, feet, nanometer, light year. Those different units are all describing the same type of quantity, length. The thing is that you will never describe length with a unit of time. You will never say the distance is 2 seconds. That doesn't make sense. And the third one is called mass, which is the m in F equals ma. So at the end of the day, anything you write down in this class should be some combination of these three different types of quantity. And if you say V equals something, then the dimension must make sense. It doesn't make sense to say like the age of me is 2 kilograms. I am 2 kilograms old. That doesn't make sense because the mass and time is completely different thing. Or you won't ask if I am 10 meters tall and she's not she, and my pufferfish is 20 kilograms heavy, who is older? It doesn't make sense because I'm comparing totally different thing. It's not even about the unit. It's not about unit conversion. It's just different type of thing. So the first thing you should check is the dimension. So now, a quick exercise. What should be the dimension of force? Your favorite thing in 9A. Multiple choice. Force is not the length. It's not the time. It's not the mass. It's a combination of them. So what should be its dimension? The hint is the Newton's law you learned. One of them is very useful. The second one, namely F equals ma. So Newton's law there's three Newton's law. The first one tells you what is the inertial frame. The second one tells you what is the force. The third one tells you some basic quality of force. A force is defined as the mass times acceleration, or it is defined as the acceleration times the mass that the force is acting on. So F equals ma. Therefore, the dimension of force should be the same as the dimension of mass times acceleration. Mass has dimension mass, so they all have an m. So the problem is, what is the dimension of acceleration? Acceleration is change of velocity per change of time. Velocity is change of length per change of time. So there's two time. So it's the change of length per time, or meter per second squared. So you know it's F equals ma, meter length over time squared. So indeed, the answer is C. Okay? Any question with this one so far? Okay? Okay, now let's apply this to our wave velocity, wave speed. So in the previous example, I'm trying to give you some formula for the speed of wave. If I'm giving you a speed of something, that something better have a dimension of length per time, distance over time. So first choice is F over mu. Force is meter length minus 2. My mistake. This should be minus 2. There's a typo. And then linear mass density is mass per length. So that's the dimension. You cancel the mass. And there's L minus 1. Minus 1 in the denominator becomes plus 1 on the numerator. So if you divide by L to the power of minus 1, it becomes multiplied by L. So here's L to the power of 2. This should be T minus 2, so that's why this is T minus 2. But you see, if someone tells you the speed of wave is tension divided by linear mass density, clearly he's wrong, because they don't even have the correct dimension. It's telling you the speed of something is some length squared divided by time squared, so obviously that's wrong. You don't even need to do a calculation. Okay? And this is important because sometimes in your final, you will do calculation yourself. And once you see you write down V equals F over mu, you know you're wrong. Don't continue. Go back and check your process, because the dimension doesn't even match. So if you take a square root, then the square root of dimension is just like the square root of other number. You just remove the square by power of 1. So the second option has the right dimension. The third one, length times g with a square root, will also have the correct dimension. So how do you know which one is the correct answer? You look at the tendency. It's very important to know what the thing you write down behave under different parameters. We learned that if you make the string tighter, the speed should increase. Here, the bottom expression doesn't change with the tension of the string at all, so you know it's not going to describe the speed of the string wave. It might describe the speed of something, but it's not string wave. And for the second one, indeed, if the tension is higher, then the speed increase. So in this case, you know that the second one might be the correct answer. You can be off by a factor of 2 or 3, but at least the dimension and tendency all make sense. So that's what I'm trying to train you in the first part of the class. Okay? Any question? Yeah. So we want to say the speed of the wave is something. The speed of wave is a speed. It should be length per time. But tension divided by linear mass density is something that has dimension of length squared divided by time squared. So there's no way something that has length equals length squared. And length and area is different. When you write down something in physics, the first thing is that the dimension must be the same. There must be same type of physical quantity. Yeah, and also L is power of 1, and here L is power of 2. So that's why in this formula, or if you look at your formula sheet, you will see the speed of string wave has a square root here, because the dimension must be length over time. If you look at just F over mu, it's going to be something like an area per time square. That's not speed. Okay? Any other question? Yeah.
Can you say why is the second one correct again?
What?
Why is the second one correct?
So, first of all, these two have different dimension. If this is area, then this is the square root of area, which is the length. So, only one of them can have the correct dimension for speed, which should be some distance over time. And you see, the first one is not distance over time. It is distance square over time square. So you take a square root and make it distance over time, which is a speed.
Yeah, but what about the third one?
What?
I'm confused about the second and third one.
Oh, well, if I tell you the string wave have a speed of its total length times gravitational constant, you see, no matter how tight you pull the string, this number doesn't change. But the speed of the string wave should increase as you pull the string tighter. So you know the tendency doesn't match. The tendency. Sometimes the dimension is correct, but tendency is wrong. So you know it's wrong. Another question? Yeah?
So when you have the three equations before, you said the first one was area and the second one was area.
That is an example because, so this one is not area, but you know, this is the same thing, but without a square root. So this is whatever this square. Okay? I just don't want to say area per time square. Okay? Any other question? Okay, good. All right, so let's look at some other type of wave. Sound is a type of wave. We won't focus too much on sound, but you should know the tendency. For sound, it's not a string, but in general, you should have a feeling that some kind of force is pulling the particle back to the equilibrium position. So some kind of force should play a role in the speed of wave, no matter what wave it is. And some kind of inertia, some kind of mass should play a role. So here, instead of using the tension of the string for sound in air, the force becomes the air pressure, and the density, and then the inertia, the mass that plays the role is just the density of air, the regular density you learn. But what is pressure? So just in case you don't know what is pressure, here's the idea. So if you have a box of air, there's a bunch of air molecules running around, and you put some piston on the top. You create some opening and put some piston on the top, then there should be some force on the piston created by the air particle because the air particle is bouncing off the piston. Now, the force on these two pistons will be different because there's more air bouncing on this piston because the area of the piston is bigger. So if you want to describe the property of just the air itself, we want something that only depends on the air, not the size of the piston. If you want to describe or you want to measure the property of this air, you might say, okay, let me put a piston here and see how hard the air is pushing me back. But then that force depends on how big the piston you choose. So to get rid of that parameter, what you do is you divide the force by the area of the piston. If you look at this quantity, which is the force on the piston divided by its area, it should be the same for both of those pistons. So That's why we define pressure. Pressure is the force on the piston divided by its area, and that will be just the property of the area itself. So if you look at the dimension, it should have the same dimension as the force by area. So you just divide the dimension by L squared, and that's the dimension of pressure. Okay? So those are some introduction of dimensional analysis. If you have more questions or you want to read more, there are some thing in the Canvas site called supplementary material. Those are some introduction I write for dimensional analysis. You can read those. All right, next, your turn. So we learned that I keep telling you, wave is not transporting matter. Nothing is actually moving away from its equilibrium position, but you do see something moving to the right. So what exactly is moving to the right? What exactly is the wave transporting? You see a wave going to the right, but my hand is not going to the right. What is going to the right? My hand is not, this is not a physical wave, but if you have a string wave, something should be going to the right. Your physical intuition is not lying. It's not the particle itself, but what is moving to the right. We see energy. Well, we know the particle is not moving to the right. MRG. NRG. What is energy? Force is moving to the right. Okay. So, the good answer here. First of all, we haven't told you what is frequency. You should not say that. I don't know what is NRG. And we can have a wave that keeps going to the right. But as you see, the string wave is going, well, that's not a good answer. Well, it's weird to say how the force moves to the right because force is an instantaneous thing. You can say right now how much force is acting on you. It's not something you can save. You don't hit a table and save all the force and then wait for it to crash later. You cannot, like, it's not a thing that you can just move to the right. But energy is something you can save. You can save energy in a battery and then you move battery to the right. That's moving energy. So energy is a good guess. Energy is a good answer. Okay. So what you have seen is wave, and most of them are something we call periodic wave. A periodic wave is something that looks like this. It doesn't have to be a specific shape, but the shape should repeat itself just forever. If you see the shape of the wave is repeating itself forever, then that's what we call a periodic wave because it's periodic. And for a periodic wave, you can define the length that it takes to repeat itself, to repeat a pattern. So you see from here to here, it takes like this long for the shape to go back to the peak. So from peak to peak, this will be what we call the wavelength of this wave. You can define the same exact length from the equilibrium position to equilibrium position. They will be the same length because the whole thing is periodic. From peak to peak, middle to middle, or bottom to bottom, all these three distances will be the same if you are looking at a periodic wave. So don't worry about which one to choose. Just choose the one that's easy, that is most easily to measure or determine. And for the bottom one, you can say this is the wavelength of the middle one. And for the bottom one, you can say from the dip to dip, that will be the wavelength. You can get the correct length from that. You can also say bottom to bottom, that will be the correct length. Those are what we call wavelengths. Okay, just some terminology. Now, more terminology. When we look at wave, the wave itself can travel to your right, but microscopically, the particle carrying those waves can be moving transverse to the direction of propagation or along the direction of propagation. On the top, you see the wave is going to your right, but the motion of the particle is up and down. These two are perpendicular. We call that a transverse wave. At the bottom, you see the wave is going to your right, and the motion of the particle is along the same direction of the wave propagation. So we call that a longitudinal wave. Just some terminology. Okay? It's not like this is transverse, this is longitudinal. If I have a string wave, or if I have a spring wave going up, then wave go up, particle go up and down, they are still longitudinal to each other. So it's not just up and down, left and right. It's how it moves respect to the direction of wave propagation. Okay? Yeah.
So you said the transverse wave, the particle is going perpendicular to the
Velocity of the wave or direction of the wave.
Right. So, and then the other one, they're in the same direction. So is there any type of wave where the propagation is going one way and the particle is going like not perpendicular or straight? Does that make sense?
Yeah, so there is. And I'll say the example I'll give you is the water wave. So you see in water wave, the particle is actually moving in circles. So water wave is not a transverse wave, it's not a longitudinal wave, it's a mix of them. And what you said, which is like diagonal, can also happen, but not if. So for this case, for what we're seeing here is a simple example. This is purely a transverse wave for the string and purely a longitudinal wave for a spring. Any other question? All right. Now, your turn. A wave always have a wavelength, true or false? I need to make sure I do a yes-no question. There's no yes-no question? What? All right, should answer true or false. If I give you a wave, I can ask for a wavelength, true or false. Come on, come on, come on. Typo. So there's a reason we call this periodic wave. Can I go back? Can I go back? The reason we call this periodic wave is because it's periodic and we can define a wavelength. If you only have a wave pulse like this is not a wavelength. I mean, this is not a periodic wave. You can have just a wave pulse, travels from here to there. It is a wave, but you cannot define a wavelength for this thing. So only a periodic wave have wavelength. Okay? Let's go, let's go, let's go, let's go. Too many animation. What? Okay, so of all the periodic wave, another terminology, this simple one that is just easy to draw is called a sinusoidal wave. You will learn that, I mean, you should have learned a sine function look like this, so that's why we call this a sinusoidal wave. Now, a wavelength is a period in space that the wave repeats itself. But a wave doesn't only repeat itself in space-wise. It also repeats its motion time-wise. So after some time, you should see the motion of the string repeat itself for a periodic wave. So right now, the ribbon is at the very lowest point that it can move in a periodic wave. What we can do is to measure the time it takes to go up and down again. See? Let's see that again. I can start the timer when it reaches the bottom and see how long it takes in time to go up and down again. And for this case, 0.91 second is the time it takes to go repeat the entire process and go back to the initial position. The time it takes for it to repeat itself is called the period of the wave. The wavelength is a length that after some distance you see the pattern again. Period is a time that after some time you see the whole thing again, repeating again. Okay? So both are some sort of period, but one is period in space, one is period in time. And usually for the time one, we just call it period. More terminology, finally. We introduce frequency. Frequency is just 1 over t. You need to memorize it because that's the definition. You have period, which is how long it takes for the wave to repeat itself. But usually when we describe like sound wave, you say the frequency of this sound is this high, then we are using frequency, which is 1 over period. In this case, if you have period 0.91, then you divide 1 by that, you get 1.10. The unit will be 1 over second, or we just call it hertz. Okay? So just some terminology. Any question? Good. So another thing we want to introduce is amplitude. If you have a periodic wave, then you say when you look at the maximum displacement it can go from the equilibrium position, we call this the amplitude. It's just from the equilibrium position to the maximum, not from the peak to valley. It's from the middle. We count it from the middle. That's what we call amplitude. Now, alright, so what if I want to write down a negative amplitude? Well, just like velocity, negative velocity just go in the opposite direction. A negative amplitude just go in the opposite direction. You will think that it is like weird to have negative amplitude, but you know you can do it. If you have a whatever formula for wave and you plug in a negative number for the amplitude, it shouldn't give you any error. It's just the same thing but in opposite direction. So if I have a wave with amplitude 5 centimeters that looks like this, then I can plug in a negative number for the amplitude and it just go opposite. The reason I want to tell you this is because it's for the same logic, same teaching reason for kinetic energy equals 1/2 mv squared. The way they teach you why there's a v squared is because velocity can be negative, but energy is always positive, so you square it. Same thing here. The energy will turn out to be square of amplitude. That's what you'll see later. So the question is, so we learned that wave carries energy. It doesn't transport matter, but it moves energy to the direction that the wave is traveling. But how many energy is carried by a single wave pulse? So how many energy is that carried by that wave? We know that if amplitude is bigger, it should create more energy because the phenomenon is just more obvious. If it carries energy and the bigger the amplitude, the bigger the wave, then it should carry more energy. But we just learned that amplitude can be negative. So we know that the energy should not be proportional to amplitude because energy is always positive. It should be proportional to amplitude squared. Just like why kinetic energy is v squared. Here, amplitude carried by a wave should be proportional to the energy carried by a wave should be proportional to amplitude squared. Okay? Everybody buy that? All right, now the next thing we should do is practice this type of question again. So E is the energy carried by a single sine wave. So a continuous sine wave can have many poles. A single sine wave is just a single sine wave. Okay? So that's what I mean by a single sine wave. If you look at a periodic wave, there's like infinite amount of wave and the energy just explodes, then it's not a it's not a well-defined thing. So that's why I asked it for a single sine wave. So let E be the energy carried by a wave. L is it's carried by a spring, so it's a spring wave. I can say the spring has a total length of L. The spring is this long, L. K is the spring constant. I hope you remember Hooke's law. A is the amplitude of the wave. When the wave is propagating, the spring is oscillating with a amplitude amplitude A. Lambda is the wavelength, and what should be the right formula for energy of the spring wave? So there are some tricks when you are doing dimensional analysis. For example, you should know what is work kinetic energy theorem, or you should know what is work equals force times distance, or work equals force times displacement. So you know, if you want something that has a dimension of energy, you can just look for a force and a length instead of breaking everything down to length, time, and mass. Why do you want to do that? Because you also know Hooke's law. You have a spring, it's annoying to analyze all the dimension, but you know if you see a spring constant multiplied by a length, that thing gives you force. So you see spring constant, length, so everything in here is basically a force. Spring constant times the length, that's a force. And if you want energy, you are just missing a length. Okay? We want typo. It shouldn't be here. There's no V. There shouldn't be a V here. All right, it's just energy. So what you want is energy. Energy is force times distance. So you should look for a distance over here. A square over lambda, that is a distance. A cube over lambda square is still a distance. But a square is the area, not a distance. So you know the last one must be wrong. Okay? Now, we have two other options, but we just learned that the energy should grow as amplitude square. If you put amplitude cube, it means that if you plug in negative number, you get negative energy. That's not possible. So the correct answer is this one. Any question? Yeah.
Is the L minus L0 period, or what is the?
So L is the total length of the spring. L naught is the natural length of the spring. Hooke's law tell you the force is the constant times the extension of the length, not just the total length. Okay? Yeah?
What was the reason behind B being wrong in terms of its wrong tendency?
Say that again?
What was the wrong tendency?
So we know amplitude should grow with amplitude, energy of the wave should grow with amplitude square.
Oh, right. I see.
So cube is wrong. The reason it's wrong is because it means your energy can be negative, but we don't deal with negative kinetic energy here. Any other question? Yeah?
How does 2 pi squared would change in this situation?
That's for second part of this course. You don't need to know why there's a 2 pi square here. And I'm guessing you don't need to know for the entire quarter because it will just be on a formula sheet. But anyway, for the first part, just focus on the physics. You know, so a number doesn't have dimension. So whatever the number you have here is just dimensionless. You don't care about the dimension, or the dimension of number is 1. So 1 times whatever becomes just that thing. Any other questions? Okay, so if we want to look at the energy of a wave, we have to say something like a single wave pulse, because for a periodic wave, there's infinite amount of wave, so the energy together is infinite. We don't want that. But if you look at the power of this wave, it should be a finite number. So for a periodic wave, it carries infinite amount of energy. It just keeps transporting energy from your left to your right. The total amount of energy transported by this wave just grows as the time you wait for the wave to just keep going to your right. But if you look at how many energy got transported per unit time, that should just be a finite number. Okay? So, because power is the energy got transported per time, it should have the same tendency for energy. So, just like energy should grow with amplitude square, the power carried by the power of this wave carrying energy should also be proportional to amplitude square. Okay? So if I ask you, instead of energy, I have power. Similar thing again, but this time a string wave. A string. Not a spring, a string. So it's just a regular string. You have frequency F, wavelength lambda, amplitude A, tension F, linear mass density mu, and you want to see what makes sense for the power of the wave. So, also the slide will be uploaded. I will not use slide for the second half. I will use chalkboard, but for the first half, I will have slide, and like I'm recording right now. Okay. So, again, there are some tricks for dimensional analysis. Instead of breaking down the power into length, time, and mass, you know it's energy per time. So just focus on what gives you energy. You learn that energy is 1/2 mv squared for kinetic energy. So energy must be mass distance squared per time squared, because speed is distance over time. So v squared, distance squared over time squared, and the mass over here. That's how you can get a dimension of energy in a really fast way. Now, power should be energy per time, so you just divide energy by another time, and you get a dimension of power. Okay? This is energy per time. Energy is this, so just give another 1/time to the dimension of energy. And if you look at this weird thing, this square root of tension times the linear mass density, you just learn that force is F equals ma, so N times A, meter per second squared. Linear mass density is mass per length. So multiply them all together, you have 2 mass, the lengths cancel, and minus 2 time. The square root just divide everything, the square root just divide every power by 2. So at the end, you know this thing, the square root of F times mu has a dimension of mass per time. So what are you missing? Power should be mass times this. This factor already gives you mass per time. So you are missing L squared and T minus 2. So what you should look for is a L squared and T minus 2 for the rest of the formula. The first part, all those 2 pi, doesn't matter because they don't carry any dimension. A number is just a number. And here we see that we want to look for something distance square and over time square. Amplitude square, good. Distance square. Frequency is 1/time. So the dimension of frequency is t to the minus 1. So you see frequency square, amplitude square, L squared T minus 2. That gives the correct correct dimension. And the first one is wrong because the first one only has 1 over T instead of 1 over T squared. You need 2 frequencies for the T square. And again, we say power or energy should be proportional to amplitude squared because otherwise it can be negative. Then you see the second one have the wrong tendency, so the only possible answer is the third one. So this thing doesn't really give you this doesn't really derive the formula. It tells you, or it gives you a way to judge how a formula should behave. Like it doesn't explain why there's a 2 pi squared, but still it's very powerful. Most of the time your mistake can be derived, or you can check your mistakes just by doing this kind of analysis. And doing this practice really tells you if you understand the physics or not. Okay? Yeah.
Are we going to be expecting questions on these midterm?
Yeah. This is exactly the question I will show in your midterm and also your homework. Any other question? And for the answer, you should. So this is not a multiple choice test. You need to explain why this dimension is wrong and why this tendency is wrong. All right. Yes. Say that again. For midterm, yes. For the final, we don't know yet. Yeah, I haven't planned that far. But for the midterm, you just need to know how to do dimensional analysis and tendency check. There will be some mathematical stuff just packaged as math question that you will learn in discussion. Any other question? Okay. Next, we have intensity. So when we look at this string wave, it's just one dimension. The wave just propagates without decreasing or increasing the amplitude. But in 3 dimensions, things becomes interesting. If you have a light source, a light is actually a wave. It's a kind of wave, it's light wave, and it carries energy. But we all have this experience that if you stay away from a light source, the brightness seems to decrease. Energy is conserved, so energy is not decreasing. But why exactly is decreasing? Why do you see the brightness decrease as you go away from light source? Light source spread wave, but in a spherical way. You have to share the energy around over the spherical surface. This is how energy got distributed when you have a light source in a point, and then it just shines light in a spherical way. So when you have a point source in 3D, the energy of the wave have to be shared by the entire 3-dimensional sphere. So the energy per area will decrease. That's why you see the brightness decrease as you go away from the light bulb or any light source. And we learned that energy is amplitude square, or it is proportional to amplitude square. So the energy got shared by the area, which is proportional to radius squared. You don't have to memorize the area of a sphere, but you know it must be proportional to radius squared because that's how the dimension makes sense. It cannot be radius cubed, not radius 1, because it has to be distance squared. So you have to share energy with radius squared. So you have to share the amplitude squared with radius squared. That means your amplitude should decrease as 1 over r in 3D. Okay? So if I ask you this question, you have a light from a star is a point source in the middle of space. Space is 3 dimensions, that's the universe we live in. And you measure the amplitude of a light wave at some distance r0. So that is my star. I measure the amplitude here at distance r0. The amplitude is a0. and I go further away to a distance r, and see how the amplitude change as we go further. Then here are some possible answers, and this will be a I-clicker question because I expect you to learn enough to know how to do it yourself now. Multiple choice, do the I-clicker, go. Try to use dimensional analysis and tendency check to see which one should be the correct relation. This delta just means approximate because there are some complicated things happening near the star, but if you are very far away, the answer should be easy. Come on, come on, come on, come on. Response, response, response. This is 3-dimension. We just learned that the amplitude should be proportional to be something. Oh, wow. Okay. So, in 3-dimension, amplitude should drop as radius 1, not 2, not 3. So that's why you should drop as radius 1, not square, not square root. Dimensional analysis doesn't give you anything because amplitude have the same dimension as amplitude. This thing is dimensionless, it's a ratio. Dimensionless, dimensionless. So all of them pass the dimensional analysis, but the tendency tells you it should be 1 over r. Okay? Any question? Okay. So here's a nice video to show you how the amplitude changes in multi-dimension besides like 1 dimension. So this is a fancy tank that if you have a lot of money, you can buy it. And then you can do some interesting physics like creating waves. This is, so far it seems like it's not worth the money, but see, you can generate something that's really random like an open sea. And you can have a wave from the outside and go to the inside. Energy is conserved, so it just explodes at the center. Okay? So in 1 dimension, the string wave seems to have the same amplitude, but in multi-dimension, because you can spread energy across the sphere, or in this case, it's a circle, so the amplitude can change as they propagate, as the energy got concentrated or spread to different area or length. Okay? All right, again, your turn. What is the brightness of light wave related to? What should it be related to? If you look at the brightness of the light, and you see some brightness, you have a feeling that this is bright, that is not so bright, this is dim, this is too dark. What exactly is affecting how bright of the light you see? So the wavelength of light will affect the color, not the brightness. So far, I mean, there is a formula you saw it earlier, which energy is related to somehow wavelengths, but this is not the case. Energy is a good answer, but as I said, energy of a periodic wave can be infinite as you expose for long enough. You don't have to look at the light and see a bunch of energy going into your eyes to tell how bright it is. You can just look at it right now. So power is the closest answer, but not exactly. The actual answer is something called intensity. It's related to power, but the power of a light source is the same. It's just there. As you go further away, though, you should see the brightness of the, let's say, the star. The brightness of the star should decrease as you go further away. But the power of the star emitting light wave should never change as you go further away. What's happening? It's the same as the amplitude decrease as you go farther away. The energy or the power have to be shared by the entire spherical surface. So the further away, the power shared by just the area of your eyeball decreases. So as you go further away, the power shared by just the single area decrease. That's called intensity. And that's why the brightness decrease as you go further away from the star. Okay? So that's why we now have intensity defined, because intensity is important. What tells you about the brightness is the intensity, not the power. Just some terminology. Okay? Okay, so let's do another thing that I expect you to do. Okay. So one thing I expect you to know is the tendency and the meaning of those physical quantities, the physics. The other thing I expect you to know by the time of midterm is how to use a calculator. There will be questions which I just give you the final formula. Power is, in the previous slide, intensity is power divided by area. I do the algebra for you. Then the distance of the star to you should equal the power divided by 4 pi times the intensity. I will do the algebra for you. You just need to plug a number. But show me you know how to plug a number and press a calculator. There is something called significant figures. That's important. You don't need to know how to do it very accurately, but at least show you know the meaning, because in physics, the amount of digits you display means something. It means how accurate you can measure or predict the result. So if you just plug in a number, your calculator will give you a long bunch of digits. Does it really mean that you can predict the distance up to as many accuracy as you have? No. Sometimes I see people write down a whole bunch of numbers, and I was like, what are you doing? So in this class, I'll just give you a simple rule. In the question, you see power 11 watt per meter square. Power 2.235. So if you see this, it means you have 4 numbers that you know is correct. You don't know how it looks like after that, but the first 4 numbers is correct. And I give you the intensity is 11. So you have 2 numbers. One is more accurate, one has less precision. And you also have pi. Pi in your calculator is 3.141596 something. It can have as many digits as you want, but are all those digits really meaningful? No, because if the next digit in intensity change a little bit, then everything behind, like the third digit, will change altogether. So when you only have 2 digits of information in the intensity, everything behind the first 2 digits is useless in your final answer on your calculator. So don't give me a whole bunch of numbers. Just keep 2. Okay? So just choose the fewest significant figure. Choose the fewest amount that appear in your test paper. I won't be very strict about this. So if you give me 1 more or 2 more extra digits, you'll be fine. But if I see a whole long bunch of number that I know you don't really understand what you're doing, then I'll mark it down. Okay? So for the calculation part, just show me how you know. Just show me you know how to use a calculator. Okay. Next thing about wave is called interference. This is what will happen if you have 2 waves coming together. They will have an interesting constructed interference. You see, initially the wave is smaller, but when they meet, they become bigger. But after that, they kind of just move on with their own life, like they never met before. You can do the same thing for opposite direction. Because they're opposite, they just sum to 0, but then they move on, like they never met. This property is called the superposition. You just add them. So what you will have to do is to predict how the wave will look like if you add them. Here are two waves that are moving closer. So before they met, you know they just keep moving. But what should happen if they actually meet? Superposition tells you that they just add up. So what you do is you draw out how the wave should look like if they are just there. But then here, you have 1, you have 2. So you have 1 plus 2 equals 3. So you know at this point, it should go up to 3. Similarly, here you should go at 0 plus 2 and 2, and then you go back to 0. Do the same thing for the rest, and then you see how the wave kind of just help each other when they meet, but then they just disappear. And this is exactly how superposition works. There's 1 plus 2. I hope you know how to do that, okay? All right, so that leads to an important thing. Sometimes you have two wave sources, and you look at the point, and because they are equally far away, the wave will end up going both up when they meet. So they will have constructed interference at that point. But for the same two wave source, you can look at different points. This point is closer to the red source. It's the same two source, but you just look at different point. Just because this is closer, you see that this wave does not have time to go back up again. So when the two waves meet, they cancel each other. What you see here is that because the distance to the two sources is different by half the wavelength, then when they meet, they cancel each other. That's called a distracted interference. On the other hand, if you have something such as a wavelength of path difference, then you see even though the blue wave have to go further, but it goes exactly one wavelength further, and that gives you constructed interference. They are the two wave sources, but you are looking at different points. So what exactly is the physical consequence of this? You can see two wave sources, and you kind of see a blurry line that the water doesn't seem to oscillate at all. Those are the points that have disrupted interference. All these lines have a lot of points. All those points have a location that causes the two waves to cancel each other when they reach there. And for constructive, it kind of just oscillates a little bit bigger, but yeah. So that's it. That's the end of this first lecture. See you Tuesday.